here we discuss about the partial derivatives of vectors. So we start by defining what we mean by partial derivative of a vector, and then provide an example to illustrate how to work or how to compute the partial derivatives. Let V which is actually depending on the variables x, y, and z, simply for this case, x, y, and z. Then the partial derivatives partial y and partial z, partial v, partial z, and given defined as partial v, partial x is given by limit a small change in x approaches 0, this difference quotient partial v, partial y, with the limit a small change in y approaches 0 of v of x, comma y plus change in y, comma z, minus v of x, y, z, or change in y, and then partial v, partial z equals to limit as change in z approaches 0, v of x, comma y, comma z plus change in z over change in z if this limit exists. So that's how we define partial derivatives of the vector function v depending on x, y, and z. So we can always define higher order derivatives, partial derivatives, e.g., the second partial derivatives of this vector with respect to x is the same as partial x or partial v partial x, while the second partial derivative of this with respect to y is partial y partial v partial y. Second partial derivatives of v with respect to z, the same as partial z of partial v partial z. And then if we define this mixed partial derivative, then this is the same way we can write it. And then the other mixed partial derivative can be written in this form. etc. So you can as well define other higher order partial derivatives of the vector b. Let's do an appetizer. If we have vector v given by 3x squared y I plus 2x y z j minus 3x power 4 y squared k find partial v partial x partial v partial y partial v partial z, and then partial squared v partial x squared and partial squared v partial x partial z. Now solution. Now remember, just the same way we explained in calculus, but to carry out partial differentiation, assuming you are doing partial differentiation with respect to x, any other variable that is not x is assumed to be a constant. Only x is taken to be a variable. Similarly, partial y, in the function you have, any variable that is not y is assumed to be a constant, and then y is only taken to be a variable. And the normal rules for ordinary differentiation still applies. So first part, partial v partial x. So this will give us 6xyi. This will give us 2yzj. And here we get negative 4 by 3 is 12, x power 3, y squared, k. So that defines partial v partial x. And then partial v partial y. This term will give us, or this component of I will give us 3x squared I this component will give us 2xz. At this point, we'll have negative. So 2 by 3 is 6. 6x power 4 y k. And then next, partial v partial z will be given by I component, there's no z, so the derivative with respect to z will be 0. So 0 I. Then j component, partial z will get 2x z, 2xy, not z. And then the j component, there is no z here, so we get 0. So this is just the same as 2xy j. Now we are expected to find the second partial derivative of v with respect to x. Remember, by definition, this is the same as partial x of partial v partial x, which is partial x, and then partial v partial x from our first part is 6xyi plus 2yzj minus 12x power 3y squared k. Now, when you differentiate this component of I, you get 6y j component, there's no x, so we get 0 j, and here we get minus 36 x squared y squared k. So therefore, the final answer will be given by 6yi minus 36 x squared y squared k. And then lastly, we were supposed to evaluate partial squared v partial x partial z. Now, from definition, it's the same as partial x of partial v partial z, which is partial x. From our calculation, partial v partial z is 2xy j. So which it turns out to be 2y j. So these are the correct solutions to that given problem. Thank you.